Hopefully you've done a little bit of work now with our 2 mole conversions that you've learned so far, where you're going to use 1 mole is equal to 6.02 times 10 to the 23rd particles, and you've also used the one where 1 mole is equal to so many grams. And remember, you're going to fill in that grams with the molar mass, and you get that molar mass from adding up the mass of each element that's in a compound, or using the molar mass from the periodic table, and that's the amount of grams in 1 mole of any substance. Now we're going to see why did we have to learn that. This is the practical application of this, and what we are actually going to be doing is termed in chemistry stoichiometry. So these calculations are called stoichiometric calculations, and this is a word that you need to know. Stoichiometry is called the calculation of quantities in chemical reactions. I guess you've noticed I still haven't found my pen that I can write on this with, so it does look like a young child wrote this. Stoichiometry is the calculation of quantities in chemical reactions, and so you're calculating if if I have so much of this reactant, how much product can I make? So it has very real-life applications. They in the nursing program, for example, it's huge. This is very much pharmaceutical calculations. It's very, very big in being able to do this kind of calculations, stoichiometry. Let's see what we're talking about. Moles of reactants and products, and then mass of reactants and products. I'm not going to spend much time with moles because that's not near as used as masses, so that's where we're going. But the single most important thing that you need to remember is these calculations are exactly identical to what we did in the last section, in section 3.5, exactly identical in every way. There's only one more step, and that step is that we are going to use the balanced equation, and in this balanced equation right here, it's saying that for every 2 moles of carbon monoxide, when you add it to 1 mole of oxygen gas, you can produce 2 moles of carbon dioxide. So this balanced equation can be used in stoichiometric calculations. For every 2 moles of this, you can react it with 1 mole of oxygen to produce 2 moles of carbon dioxide. This can be a conversion factor, and the single most important thing that you need to remember in stoichiometric calculations is the first conversion factor that you need to try to remember to write needs to come from the balanced equation. This is saying that for every 2 moles, it's like a recipe, for every 2 moles of carbon monoxide, I can make 2 moles of carbon dioxide. Now, yes, I got to add some oxygen in there too, but for this particular problem, I don't care about the oxygen. I just care about my carbon monoxide and carbon dioxide. I often think about this as baking. Let's say I wanted to bake some chocolate chip cookies for my adoring online chemistry students. If I had all the ingredients at my home, I would need to put them together in the proper ratio to be able to produce a good cookie. And I made a lot of cookies in my time, and I know the recipe almost from by heart. That's on the back of the Toll House, Nestle Toll House bag. 2 1/4 cups of flour. I mean, I know that thing. That's how many chocolate chip cookies I've made. Now, if you don't put it in the right ratio, you can tweak what those cookies taste like. You can make them more chewy, more crunchy, however you want. However, if you leave out the eggs, and if I want to increase or decrease that recipe, I also need to increase or decrease the number of eggs, because those cookies are not going to turn out without the eggs. So if I want to double my recipe, I've got to double my eggs. If I want to triple my recipe, I've got to triple the eggs. And we do that all the time in our everyday life. And we use this equation, our balanced equation, to help us with that. That's how I want you to think about this. So let's work on this problem right here. They've written on this next slide for you, they wrote some examples of how you can write that as a conversion factor, but this is what I want us to sit on right here. Again, I really wish that the writers of this textbook would show you the process that it goes through, and I'm going to take the time to do that. I would like for you to see that what is our given here? The same reaction. We have 2 moles of carbon monoxide. So I'm going to just insert a piece of paper here. If we have 3.82 moles of carbon monoxide, and we're going to use our balanced equation that said for every 2, here's our balanced equation, plus O2 goes to CO2. What is our given in this? Well, our given in this is 3.82 moles of carbon monoxide. Our unknown in this case is moles of CO2. How much CO2 does it take if we want to make that much CO? Well, what's our con factor going to be? Here's the only new thing in this whole section. The only new thing. You're going to take your balanced equation, these coefficients. Oops, that's not balanced. I need a 2 in front of there. You're going to use those balanced coefficients as your very first con factor. That says, just like baking those chocolate chip cookies, for every 2 moles of carbon monoxide that I start with, I can make 2 moles of CO2. That's what the equation says. Now I can use this as a con factor to get me from one to the other. Okay? And I'm going to ask myself my same 2 questions that I always ask myself. Am I ready to solve? And the answer to that is, well, let's see. Do I have a conversion factor that says moles of CO? Moles of CO. Do I have a conversion factor that says moles of CO2? There's moles of CO2. So my answer is yes. I'm ready to solve. And you're always going to solve by starting with your given. So here's my 3.82 moles of CO. And I have moles of CO on top, so I'm going to put this moles of CO right here in the denominator, 2 moles of CO in the denominator, and that forces this 2 moles of CO2 to be in the numerator. Now, it just so happens, students, that this time the coefficients in front were both 2's. That's not always going to happen. It's not always going to happen. So whatever it is, you're going to put that coefficient. If this was a 1, remember, like this coefficient here is an understood 1. If it's a 1, you're going to put a 1. If it's a 3, whatever it is, you're going to put that in front. Now then, since this is a 2 on top and a 2 on the bottom, they'll cancel out just like in math. 2 divided by 2 is 1, so it goes away. So I can make, and this mole of CO takes out that mole of CO, and I'm left with 3.82 mole of CO2. And now I have gone from moles of my given to moles of my unknown. So I've changed from carbon monoxide, which will kill you, into moles of carbon dioxide, which plants take in as their energy source. So this is an important thing, and we're going to continue to work with this. This is no different than what you were doing with that one extra step. So please don't make it harder than it is. I'm not saying that it's easy. It's not easy, but it's not as hard as it could be. And you can see that they also did the exact same calculation with what about how much oxygen do you need? Well, they're given this time is still moles of CO. But notice what their com factor is this time. This time, their com factor that they did not show as a com factor, and I really think it's extremely helpful for you to have that showing that that con factor is for every 1 mole of O2, I need 2 moles of CO. And where did that come from? Where did these two numbers right here come from? They came from that balanced equation that said 2 mole of CO plus O2 goes to 2 moles of CO2. That's where it came from. So this con factor right here, I didn't even spell con factor right, look at that. This con factor, conversion factor, that's what that stands for. This conversion factor came from this 2 right here, from the CO, and this 1 right here, okay? That's exactly where it came from. That's where this 1 mole of oxygen came from, and that's where this 2 moles of CO came from right here. It's from this balanced equation. I don't know why I put that mole up there. All right, that's where it came from. Everything else is just exactly like what we did before. Now, can you have more than one? What if I don't want moles? How many times do you go to the store and say, give me a mole of this or a mole of that? You don't. And you don't go to the lab and use moles. You use grams. So you can do this exact same thing, only let's add another con factor or 2, and let's now go from moles to grams. And by now I hope you know how to do that. I hope you know how to go from moles to grams. Okay. This next slide gives you a practical example. I'm going to see if it's asking you. This is in your textbook on page 99, talking about urea can be synthesized in the laboratory by a combination of ammonia and carbon dioxide, and it gives you the equation. 2 ammonias with 1 carbon dioxide produces ammonia. This is urea right here, and then water. That's the chemical equation for urea right there, and then water. And it asks you to calculate the amount of urea that's produced. And I'm going to let you work through that one. You can see how it's worked out for you in the textbook on page 99, because I want us to work with one that's got mass in it. That's what I want us to spend the rest of our time on today. Section right here, this one talks about the balanced equations right here. Give us the amounts of reactants and products in terms of mole. However, when we're weighing them in the lab, we're going to use grams. So that's what we're going to work with now. So here's nitrous oxide, which is commonly used as an anesthetic, and I don't want to use nitrous oxide. I wish that she would use the correct name of that. That's dinitrogen monoxide, used as an anesthetic in dentistry, manufactured with ammonium nitrate. So there's ammonium nitrate, and there is your dinitrogen monoxide and your water. Calculate the mass of ammonium nitrate that must be heated in order to produce, we want 10 grams. So if we're going to make 10 grams of that, then how would we go about it? So again, let's get this equation in our mind, this balanced equation right here, and then let's work it out. And we're going to work it out on paper. Okay, so if we were to work this one out on paper, and this one is in your textbook, this was on page 100 in your textbook, and it tells you you have ammonium nitrate. When it's heated, this triangle symbol above your yield sign means it's heated. And it asks us to calculate the mass of ammonium nitrate that must be heated in order to produce. So our given here is 10.0 grams of N2O. And it's asking us how many grams of ammonium nitrate. Again, I am doing the practice problem that's on page 100 in your text. That's what our unknown is. So we need some cofactors here. And the only difference in what we've been doing in the previous sections is that first cofactor that you need to worry about. And the way that you can look at this is I need to look in my balanced equation at two things. What is my given and what is my unknown? And that's all I'm going to care about. So my given, oops, I pushed the wrong button. I don't know. I'm so sorry about that delay. We're going to go right back to the N2O in our balanced equations right there, and then the NH, oh, I gotta stop doing that. The NH4NO3 ammonium nitrate is right here. And in front of each of these, the balanced equation has ones in front of each of those. There's no coefficient in front. It is an understood one. So we have 1 mole of NH4NO3, because there's nothing in front of here, it's an understood one, equals 1 mole of N2O. There's a 1 in front, understood 1 in front of there. That's our first conversion factor. That lets us go from N2O to NH4NO3. That lets us go from one substance to another. All right? Now, are we ready to solve yet? That answer would have to be no, because the next thing that we're supposed to ask ourselves is, do we have a conversion factor that says grams of N2O? And we do not. We have moles of N2O, but not grams of N2O. So we need a conversion factor that's got grams of N2O. So we're going to say 1 mole of N2O equals so many grams of N2O. And you know you're going to fill in this blank with its molar mass. Y'all remember how to find molar mass. We've worked on that already. We know nitrogen. We've got 2 nitrogens. Each one of them is 14.01. I got that from the chart. And we have 1 oxygen, and it's 16.00. So that's 28.02 plus 16. And 28 plus 16 is 44. So it's 44.02 grams. Okay? And then I'm going to do the exact same thing for every 1 mole of ammonium nitrate. We have so many grams. of ammonium nitrate. And we're going to do the same thing. We have 2 nitrogens, and so that's 28.02 or 14.01 times 2. And we have 4 hydrogens, so that's 4.04. And we have 3 oxygens. Each one is 16. 16 times 3 is 48. Add those together, and I got 80.06. Okay, and so that's exactly what you're going to take right there. And now you're ready, because now we have a conversion factor right here. Now we have a conversion factor that says what we're looking for in our given, grams of N2O. Now we have a conversion factor that says grams of NH4NO3. So now we are ready to solve. And we're going to solve by starting with our given. And so you're going to then say 10.00. I don't know if I have room on this. We're going to say 10.0 grams of N2O. And since we have grams of N2O on top, where are we going to put it over here? We're going to put our grams of N2O on the bottom, which is this conversion. It's not the first one that we wrote, but it's the first one that we're going to use because it has the right units. Okay? You see how that works. And I think I better just stop for now and move on. I believe you can follow the rest of that one, how it's done in your textbook, using those grams. And she does it in steps, which I much prefer going all in one straight line. I think it's less confusing to do it like that. So I hope that this is helpful to you. And I'm going to give you several to do like that, and I think I'm going to give you another PowerPoint as well. Not a PowerPoint, but a video that just does it on its own. I'm going to send you lots to choose from, I think, on this one.